What's the big theorem that tells you if a series is uniformly convergent? A series being a sequence of partial sums. The theorem deals with uniform convergence as a property of sequences of functions. Partial sums are functions in a sequence. They're all strung out, and this thing is the limit of a sequence of partial sums, all of which are continuous. How do I decide if the convergence is uniform? The Weierstrass M test, right? If you can find, and how does the M test go? On some set of real numbers, if f of x is no greater than, fn of x is no greater than mn. So this is the majorizing number for fn of x, right? For any x in E. This is the uniform part. X can be anywhere in E, and this is true. Then, if the MNs converge, that implies that the FNs converge uniformly to the limit, the sum of the Fn of x. So these things, if we can get them dominated by a constant m sub n, and the sum of the constants from 1 to infinity converges, then this pointwise limit of these things is the uniform limit of the Fn. Okay? So what would be a good candidate here? Remember, Fn of x is f0 of 4 to the n x over 4 to the n. Is that always going to be less than or equal to 1 over 2 times 4 to the n? I think so, isn't it? F0 is never bigger than 1/2. It's always positive, never bigger than 1/2. So there's the 1/2. And then I'm dividing by 4 to the n, there's the 4 to the n. I don't think for any x, for any real x, this is always going to be true, isn't it? So what's this? If I let that be the m sub n, what's the sum of the mn's? And I better go from 0 to 2. You can factor out the 1/2. It's in every term, and then I have 1/2 sum n equals 0 to infinity, 4 to the minus n. That's a geometric series with constant ratio 1/4 and initial term 1. So the sum of that thing is 1/2 times 1 over 1 minus a quarter, right? 4/3. Is that 2/3? 2/3? 2/3. Well, looks like the MNs form a convergent series. What's that mean in terms of the FNs? They must converge uniformly to their limit F. So this establishes, via the Weierstrass M test, which will be proven Tuesday, given what that is here. It's not a terribly difficult proof, but basically this is what once you capture the FNs by putting a constant m sub n above them, and the MNs are well behaved enough to converge as a series, then you sort of have the FNs under control. That's basically it. So the convergence is uniform. I have now a uniformly convergent sequence of continuous partial sums, therefore they must converge to a continuous function by the theorem. So the van der Waals function, the Takagi function, and the Blancmange function, whatever you like to call it, this thing is continuous by that argument. We accepting of that thing? Does that look okay? The FNs are getting shorter and shorter, more teeth. Add them all up, and because they're getting short so fast, we can put that MN on top of it. The MNs converge, so for any x in the domain of the function, it converges pointwise to the phi function. Okay? Nobody's too impressed with this. This is supposed to be refreshed. This is culture. I'm doing you a lot of favors here. Instead of having to read that in a book, it's scribbled. I'll explain this. Are we now in agreement that this function seems to be continuous?
Yes, sir.
Okay, good. That's what we want to hear. Yes, sir. Sir. Yes, sir. Okay. Now, why the hell isn't it differential?
Why isn't it?
Yes, it's nowhere differential. Nowhere differential. Here, in fact, for your viewing pleasure, I have actually written that at the very outset. Continuous, nowhere differential. Okay. I forgot that already. Okay. So there's F0 and F1. And let me just, this is going to be just a piece of F2. Okay? And of course it keeps going. And the whole damn thing goes all over the real axis as well. All right. I claim that if I set delta sub m equal to 1 over 4 to the m plus 1, then I'm going to make that plus or minus. I can go either way, a step of size 4 to the m plus 1. 1 over 4 to the m plus 1. Then f sub m of x plus delta m minus f sub m of x is plus or minus delta m. Let's see why that's true. Remember, delta m is 1/4 of the base of a sawtooth defined by f sub m. Right? So this guy is f0, this guy is f1, and this guy is f2. So, for example, if m is 1, what I'm saying is I take, no matter where I am, if I'm right here at x, say this is a typical x, if I trace it up to the sawtooth, I either have to be more than halfway away from the peak or the valley, right? For some x, I mean, it could be on the downswing too, but the point is, I guess I could be dead in the middle. That would be okay, but then a step of size 1 over 4 to the m plus 1 would take me up to the peak or exactly down to the valley, right? It's 4 units across for m plus 1, right? 1 over 4 to the m plus 1. The next one, F3, would split this into 4 pieces. Okay? I already have an up side of the tooth and a down side. Halfway up is 1/4, full way up is 2/4, halfway down there's 3/4, all the way down is 4/4, right? So if I'm at any x, in principle, I can either go up or down a step of this size, right?